All right. So we're going to start looking to that transfer learning. We've seen this idea already. In fact, it's the thing that we started this whole course with, particularly with something like Word2Vec. So we've discussed how when you're doing some kind of text classification model or even language modeling, there is a question around how do we start with decent word embeddings? How do we start with some kind of representation of words that is semantically meaningful, not just a representation of the word like a one-hot representation would be. And so we've kind of seen that there are at least three things that we've really come to. The first is I make an embedding layer and I throw that into a neural network as the first layer of my pipeline, but then I have to just train that from scratch. The alternative is that I do something like a Word2Vec, which then gives me that pre-trained embedding first layer. And then I just use that, but with frozen weights, right? So now I cannot change the representation of words based on the task. It just uses these kind of token embeddings so that we can just kind of start working with at least words that have semantic meaning. And then the neural network must figure out how to use that for its own ends. And then lastly, we saw that there was this intermediate step where I start with some Word2Vec embeddings. So at least now I have general semantic meaning in my words, but then I still fine tune it and allow the neural network to back propagate all the way into my embedding layer. And that was that kind of middle level there, or kind of shown at the bottom, the third point there. And that was called fine tuning, right? So we take what is called a pre-trained set of embeddings. So pre-trained, we've trained them previously to the current model, and then we fine tune them as in we make them more specific to the goal in hand, all right? So what data do we have for these different tasks? So if all we're going to do is train from scratch, then we're not going to have a ton of data. It's not going to be particularly diverse. If all we're doing is rating reviews from IMDb, they're all going to be about movies. They're all going to be in the last, probably 20 years, probably. They're all going to be a particular length and tone. They're all going to have the same kind of label structure that matches IMDb's labeling, and so on. So it's not going to be a huge data set. It's not going to be particularly diverse, but we know that the embeddings we get out are going to be really, really useful for the tasks we want, right? They're going to be super, super tuned towards identifying good movies, identifying bad movies, and providing particular ratings for those movies. All right. Then on the other side, if we just use pre-training or, kind of Word2Vec kind of things, well, then we can use a whole bunch of data. We can throw all of Wikipedia in there, and we don't have to label this data. You obviously just take the two words on either side of a vocal word if you're doing Word2Vec, and that is immediately the labels of my data. So it's really, really easy for me to generate a whole bunch of, context, input context pairs for that. And so then I can generate a lot of data. It can be diverse. It doesn't just have to be Harry Potter, of course. We can show as much data as we care or need to. Okay. And in this case now, the domain is general. So it's going to be about general language, the English language as a whole, not just the English language when applied to rating movies or when applied to Harry Potter. Okay. But now if we consider what's happening in the middle, well, so if we're training it from scratch, then there may not be enough relationships in the words, all right? So we may not actually get a really particularly good representation of language. If you're just using the pre-trained ones, then you'll know the representation of words, but you might not then end up getting representations that are useful. So for example, if your task is to predict the capital of a particular country or do some kind of very specific domain-centric question answering kind of style, then we may not get representations of words that are as informative to that as possible, right? When I get a representation of Spain and a representation of Madrid, they're not going to be sitting next to each other, or they may not be a perfect vector's distance away from each other, or that vector may be rotated in some kind of really large semantic ambient space. And so now it's a complicated thing to try and tease apart. Whereas if we have very specific word embeddings, then the token for Spain and the token for Madrid are just going to sit on top of each other. If Madrid isn't for some reason the capital of Spain, I'm sorry. I didn't check that example first. All right, so now we're going to get these tokens that are far too general for what we want to do with it, but at least they are general enough to actually understand and kind of have a really rich semantic structure. And then the Holy Grail, obviously what we've spoken about before and what you could have guessed, is I'm going to take my really rich semantic structure, I'm going to start with that, and then I'm going to let it fine-tune to be a lot more relevant to the task at hand. So for example, the fact that Madrid is the capital of Spain was probably still represented in the general Word2Vec training, right? We did see that sort of thing. That was one of the examples we made. There was that paper that even showed this. Okay, But now, if that is a representation that exists in the Word2Vec, we want to make it more prevalent. We want to make it show up more so that the task for our neural network becomes easier. And so then you're going to fine train it on this task specific data. All right, so you take a Word2Vec that was trained on Wikipedia, you throw it into a neural network, and then allow the IMBD task of providing numerical ratings to backpropagate through it. Okay, that is known as transfer. So you take knowledge from one corpus or from one task, all right, and you transfer it to an entirely new corpus or an entirely new task, all right? And I know it says we'll learn more about this in the course. We won't, we will learn about it now. Okay, so you're going to take your source task, you're going to pass it in through an auxiliary model. The auxiliary model in one case is a Word2Vec. And then you're just going to take that knowledge, and in this case, knowledge is the parameters of your embedding layer, it's the parameters of a neural network, or some other representation that has been tuned by the data. You pass that into your downstream model, which is probably a transformer, and then you get an output target task off the top of it. All right. So this isn't a data flow pipeline. This is a training flow pipeline. All right. So I start with the first task. I collect data for that task. I then go and apply it and use that to fine tune one model that has certain properties that make it better at learning language. So for example, why would we start with Word2Vec? Why does Word2Vec give us better language representation or word representations than a fine-tuned transformer maybe? And the reason for that is because the task is somewhat harder, and because the task it does is a lot more geared towards language understanding. To be able to predict your context words requires semantic knowledge that is very general. To be able to predict the rating associated to a particular IMBD review does not. It just requires you to recognize a handful of words that show a degree of positivity. So for example, if you see the word great, you're probably going to give it a 7. If you see really great, maybe now it's an 8. All right. If you see the word cat, it's a 10. And so you can keep kind of then only looking for specific words in your main model, but the general auxiliary model now needs to do something harder, but at least we can then use a lot more data to get those representations. Okay, everyone following so far? I know this is pretty bog standard, but we good? Okay, and so there's a couple different, at least according to Sebastian Rudder, there's a couple different types of transfer learning. I don't really know about this taxonomy, but I think it's useful to think around the different ways that it can be used. Okay, so for example, there's transfer learning. If we descend down the left or the right side, we get transductive learning on the left and inductive learning on the right. The key part about the transductive category here is that the task is going to be the same, and we're going to use the labels from the source task. All right. Why does the task say the same? Because we're using the same labels as the source task. But we can either use different domains or completely different language. So for example, if I am doing sentiment analysis, that the labels will still stay the same. It's still going to be positive, neutral, negative, right? But I might be able to do sentiment analysis in Spanish or English or French or Yoruba. And then in that case, I have cross-lingual learning. But hopefully, if we have a model that is doing a really good job, it can reuse some of the semantic information, the semantic space from French, and try and map Yoruba into that same semantic space. Now, obviously, families of language exist, different kind of regions have built up similar languages. So it's going to be much, much easier to go from Italian to French than it is to go from Yoruba to French. But the idea here is that at least we can reuse something. All right. Down the left side is domain adaptation. So in that case, the labels stay the same, the language is the same. We're just doing different domains. So you can still do sentiment analysis, but maybe I'm taking data from Twitter or X or whatever, or instead of Facebook, or let's say X instead of LinkedIn, right? Obviously, the way people speak on those different social media platforms is very different. They kind of engage with it differently. They have different policies. And so now there is a degree of domain shift, right? No one's going to go onto LinkedIn and say, like, I'm totally stoked. Probably not. They want to be professional, right? So the kinds of language they're using differs. If they are 10 out of 10 happy about something on LinkedIn, they're going to say, I'm very excited and really pleased to announce, right? Like we've all seen LinkedIn posts. Whereas on X, they might then say something a little bit more dramatic, and actually the sentiment or like the valence around it is somewhat less. Okay, but again, at least we have something of semantic space to start with by having word representations from X that we can then just learn to change the mapping out of those words from LinkedIn. Okay, so that's transductive, saying task, different input languages or different kind of sources of text. Then down the right side, the inductive version, they have different tasks. And so now you have to actually change the labels you're using. So you use the target task labels. And so now either we're training these different tasks at the same time or we're training them in sequence. And that's the kind of big distinction here. So if they're being trained at the same time, then that's called multitask learning. And if you train them in sequence, then it's called actual sequential transfer learning. That latter one, the sequential transfer learning in this case, is the more common version. Generally, the ideas since 2019 have changed where anything to do with multitask learning in NLP these days is just considered one really big task, and then you kind of just work off there. So that line is a little bit blurry at the moment. But if it's sequential, it's really clear. In that case, I am doing sentiment analysis to start. And then I am doing classification of movie ratings. And then after that, I'm going to do language prediction, like actual language modeling. And then I'm going to do question answering. And you can try and stage these tasks in ways that at least make language more likely to emerge as it goes. There is obviously the reverse way, where you can start with something like language modeling and then end up doing a classification task after that. And that's actually the version we're going to look at mostly today. All right. We're all comfortable with these different versions? They're clear? Cool. Guys online, are we happy? Yeah. So we're going to look at our first model today. And so this lecture does become a little bit, number one, it starts with like some kind of case studies, I guess, of models, which we do need to know the details of, more just so that they can inform how we approach our own modeling and the ideas in the field. And then towards the end, it also becomes a little bit more like a few different ideas that are pulled into one lecture here. Mainly just so that we get the full breadth of ideas around how we use transfer learning and how you can use different information. This course has changed a little bit this year. Last year, this was like the main thing they were doing in their project. So it was a little bit of a bigger lecture then. Anyway, so what we're going to recap now is just kind of how you get these word embeddings in the middle there. Okay, so usually, obviously, we train from scratch, but now you can start with something like love or word to vec. You get these word embeddings. You can see the difference between the picture on the left and the right. It's just that those dots are colored in, showing that now at least there is some magnitude to those vectors. And so we actually represent some kind of information with them, whereas on the left, they all start close to zero or whatever. Okay, but now in this case, we are training the same model. The only difference is that the kind of way we initialize those weights, the kind of start weights on your embedding layer at the start of your downstream training is different. But there's actually a really cool another way to do it. You can actually get something a little bit more tailored towards language modeling and something a little bit more kind of, from first principles that we can do in our model. And that is what was ultimately called ELMO. Okay. So in this case, representations of words are represented in the current context. It's not only words, but also how you process a sentence is now kind of learned and baked into the process of ELMO. All right. There's a little bit tricky or weird way of doing it, so we'll go through it slowly, and you can stop me if you have any questions. So we're going to start with some token embeddings. Again, we want to train them. All right. And that's what now ELMO is going to do. It is going to produce these pre-trained token embeddings. And to start, it's going to take every letter in our word. So you take all of the letters in a token, split it into its different letters, and we pass that into a new neural network, right? So it's a character level CNN plus this thing called the highway block, which is essentially a skip connection. Okay, so the character level CNN makes it possible to represent even unknown words. It's a similar idea to why we use BPE and not tokens per word, why we don't just token by white space. Because in that case, we have a fixed dimensional dictionary, whereas if we use BPE and we have subword tokens and subword tokenization, you can at least put subwords together. The idea of ELMO, at least the kind of principle of ELMO, is that we're going to do this completely from the most atomic units we can, which is the individual letters within our tokens. All right. And so now it tells a network which words are written similarly based on the various letters. And then hopefully from there, we can immediately start to build up some kind of token representation and get information out of that. If not, again, neural networks are somewhat nice in the fact that they fail fairly gracefully. So if there is no good information to be found in the letters, it's just going to output something like a random vector in that case. And so it's still informative to your model. There is still no better idea if the letters are uninformative anyway. All right. You're still going to be able to then back propagate off of those embedding layers. Okay. So let's zoom in and see exactly what's going on for each letter. So number one, we take in these letters at the bottom here, and now you have a letter level of embeddings, and you just do a convolution followed by a global max pooling on that. All right. So same ideas. We've seen both of those operations before, and we know that we can back propagate through them, even the global max pooling. Okay. So this is at least trainable by back propagation. And then from here, we get into what's called this highway block, and there are two of them in sequence. And again, it's a little bit weird, but it should look pretty familiar because it is actually kind of like a little transformer block. So what we're going to do is you're going to take the representation of this word after the convolution and max pooling, and you're going to apply a linear layer plus a bias, right? So this is X over here. You take your linear layer plus your bias. That is then going to go through a sigmoid activation. All right, that's what that one means there. All right. And then that is going to give us a value between 0 and 1. That is going to work like a gate. All right. So now we have G over here and 1 minus G over there. Because there are two of them, they now sum to 1. Essentially, the sigmoid is working like a probability distribution or some kind of linear interpolation between these two pathways. Either I can go along the right side, okay, or I can go down the middle. And in this case, and in most cases, you're going to be somewhere in between. Okay. The middle path is just going to do another linear mapping, all right, and then rescale that by our gating variable, by the scalar variable we got from G, all right, and then over here, we are then going to just take our original representation for X, multiply it by 1 minus G, and then just add it back at the end, all right. So ultimately, what we're doing is we're taking W times by X. All right, that's this green pathway over there. And then we're adding back in X. All right, and that's the blue pathway over here. And then we just need to do our different weightings, which is 1 minus G over there and G over there. Okay, that is the full highway block after that. That gives us another vector representation, the same size over there. Obviously, because we have a skip connection in blue here, we can't be changing the vector sizes, all right? So we know that the linear projection has to be square so that we can actually do that addition at the end. Okay, and then from there, you just do a linear projection onto the embedding size that you want. All right, so that goes over there. All right, I should go the other way around, but you know what I mean. All right, is that operation clear? You guys don't seem convinced. Which part of this is not clear? Nine people online. Which part is are we not happy with here?
Hi.
Yep.
The G part, the 1 minus G part, I didn't quite get that like operation, what's happening there. Can you please repeat that?
Yeah. Okay. So G here is the output of a sigmoid distribution. So that looks like this. Okay, where that is 0.5. All right, and then the top goes to 1, and then the bottom is 0. You're comfortable with that being a sigmoid distribution?
Yes.
That's sigmoid of X. All right. So that is going to give us a value between 0 and 1, which is a weighting in this case, right? Because it interpolates between the left path or the right path. So what we're going to do is say, take my input X, all right, which is the output of this character level CNN plus max pooling. So we're going to take that X, and you're going to apply this operation to it, all right? It's just a one-layer neural network, and then the sigmoid acting on it. So in this case, you have your vector representation here, 0, 0. You're going to multiply that by some weight matrix W, all right? That's there. And then you're going to add back B. Okay, that's that. So you do affine transformation if you want to keep it mathy, and then that's going to give you now ultimately a new vector of the same size as original. And then you apply the sigmoid to that individually, right? So you apply that S-shaped function to each vector individually. Okay, and then that will tell us how much we're interpolating for each dimension of this vector, all right? Are you comfortable up to there?
Yes, yes.
Cool. All right, so I think maybe the one part that I didn't make clear enough the first time, so this was good, is it is on a per dimension basis with that vector, right? So that's a G for every dimension of your vector there.
Yes.
All right, so then that tells us how much we want to just skip. All right, so 1 minus G. So if it's 0.5, if my sigmoid was sitting at 0, where there's no kind of use in one way or another, then it's just going to balance them. All right, it's just going to say, well, half of my representation should just come from the character level CNN, and the other half should come from this linear projection over there. All right, and this linear projection is different to that one. All right, they are different weight matrices. This is its own projection that's learned. So that's WX on its own there.
Oh, I see. Thank
And
you.
then that's going to be multiplied by its weighting, G. Again, G is now acting on every dimension. And you go 1 minus G. And then you just add back X to start. Right, and that's this pathway here. Does that settle the ideas a bit?
Yes. Do you mind just the equation that you just wrote there? So the G and the WX, the first term is from the linear layer, right?
Yeah, the one in green. Yes, that's the linear projection. Yes.
And then the 1 minus G times X is from the G gate on the right hand side, right? I don't know.
Correct. 1 minus G. Yeah, exactly.
Okay. So why are we multiplying it by X again before we're adding? Like,
So
don't get.
yeah. So I mean, that's just also what the diagram is saying, right? You can see X is over here. It's forking over there.
Okay,
And then this product there, that's like this multiplication over here, right? That's what this X is showing there.
Yes, I see it now. Sorry, thank you.
No worries. All right, cool. Yeah, thank you for pointing that out. All right, so that's the highway block. Okay, so that's how we get representations for each token. You can train that little module, you can train this little neural network to give us good word embeddings, right? From there, Elmo then takes that, kind of repeated application of this character level CNN and highway block for each word. So it's going to be reused for each token there, and there. All right, number one, that's great. We love reuse in our models. Why? Because that means that every word I get is now training that CNN, right? That is now going to help me learn that really, really quickly. And then on top of that, we do the usual thing we've seen a few weeks ago. You take a 2-layer LSTM, so a recurrent neural network. We don't need to go into the LSTM side, like the forgetting and stuff. You take a 2-layer recurrent neural network. You do one going from left to right. So that's shown on the left. And then you do one going from right to left in green. All right. And you take those models and you let them predict the next word they're going to see. So if we're going from left to right, obviously they are predicting the sentence as it would follow naturally. Whereas if you're going right to left, you start by reading your E of S token, using that to make a prediction for the next token you're going to see. So the full stop, then you read that in and use that to make a prediction for kitten and so on. All right. So you do the language modeling, but you do the language modeling where you're producing the sentence backwards. Okay. You train these two language models separately. All right, they are not connecting at the moment. There's just a forward LSTM, a forward recurrent neural network with 2 layers to it, and a backward LSTM with 2 layers to it. But it is the same recurrent neural network you've seen for language modeling a kind of few weeks ago. But now what it's going to do is it's going to take all of these different levels of our neural network. So it takes our initial embedding. It takes our initial embedding at the bottom, so that's layer 0. So that's saying, well, maybe what this character level CNN plus highway block, maybe that was just sufficient to get nice embeddings. So I want to give it that ability to just remember that. So we're going to say, take layer 0, then take the first layer from your 2 LSTMs, So over here from your two recurrent neural networks, those two layers, and we're going to concatenate them. All right. Then we're going to take the two second layers from our two LSTMs, the one forward and one back, over there and over there. And then now they are being concatenated here. Okay, so we have our layer 0 representations of the words, we have our layer 1 representation of the words, and we have our layer 2 representation of the words. Does anyone want to remind me why we might want to do a forward and a backward recurrent neural net? Sorry?
Memory bias going forward from the previous.
Yeah, it's biased towards remembering the most recent words it's seen. So how does going kind of both ways fix that? Which will it forget if it just did the forward LSTM?
Just want to forget the first.
Okay, and then that's the one that the backward LSTM will remember the most, right? There we go. Thanks. Cool. Okay, so we should, in theory, by concatenating those two representations, have a model that is biased towards representing all words fairly well. Again, transformers show, or the successive transformers show that maybe wasn't true. In addition to this, having to do an actual rollout is a slow operation for these recurrent nets. So another reason why transformers are just more used than recurrent nets is computational. They can be run in parallel, whereas recurrent nets cannot. They're sequential models. Okay, so what we're going to do is we're going to take all three layers of our representations and multiply them by these lambda variables. And the important thing is these lambda variables are ultimately going to become task specific. All right. And what they're now going to do is they're going to take all three of those representations, scale them by the lambda, and then add them together. So we have another kind of linear mixture of our representations. And so hopefully, again, this will allow us to now represent a richer kind of word embedding. All right. If we need it really detailed, if there was like a really difficult word to build up the semantic representation for, then maybe we needed 2 layers to do it. Maybe the word could be represented just in terms of its letters. Words like I, the full stop, those sorts of things don't need further processing. They are pretty atomic in their own right. Names are considered this in language. They are considered arbitrarily compositional within a language, meaning that they do not need, they do not come with their own information. They need to be in context to gain any sort of information. All right. So if I say Devon, you know, that means nothing, obviously mapping onto me, but the name Devon means nothing, right? There's no consistent semantic. I know humans say, oh, all, you know, Jareds are bad people or whatever, but that's not actually true within the laws of language, right? So that might be why you want to use the layer 0 representation, is because names and you know, kind of the smallest words within our language, the most frequently used ones, don't tend to be semantically meaningful. You don't need depth to process them. Whereas the word, you know, kitten or saw might only need one level of processing, but at least it allows us to build up a richer semantic in the first layer of our LSTMs. And then again, we can do the more rich, more difficult processing in the second one. And it's up to the neural network and the data to decide what it uses, because it can set that to 0. If there's no good reason to use these representations, the neural network can choose not to. That's not how neural networks behave. In almost any case, they always are biased towards using information. They can always pretty much correlate any sort of non-noise information to another variable. That is their problem. That is called overfitting. So we do have that issue here. But the data can try and restrict that. And the idea is if we have enough data, which is the point of pre-training, we can get away from that. All right. So let's put this back into context. That was the Elmo embedding model. In the past, we just used word-to-vec and glove and those sorts of things. But now we have Elmo. So you take in all the words, and then Elmo is a learned way of representing these tokens, but with a much richer architecture than something like word-to-vec. Okay? And so we use a huge unlabeled data set to learn not only words, but how to process the entire text, or how to use the entire text to come to a word embedding. All right? So this very much places that emphasis on words are meaningless outside of context, or that we need this distributional hypothesis to determine the meaning of words. The nice thing about Elmo is it puts it into the start, rather than actually relying on the neural network to figure it out for a particular task. I see a hands up.
Can you go back to the slide where we're adding the 2 layers and the initial embedding? Yes. So after we concatenate the 2 layers, are those compressed before we add in? Because from the number of dots, they seem like they have like different dimensions. So I'm a bit
Yeah,
confused.
no, you'd have to choose the number of dots that they matched.
Oh, okay, I see. Thank you.
Yeah, no worries. I mean, and you're correct. If you didn't have that, then you could do a projection down to the desired size. The only problem is then you have to learn that projection, right? In which case, you'd have another weight matrix sitting there and there.
Okay.
But you're thinking the right way. Cool. Sorry, was that the only question on that slide?
Yes.
Cool. All right, and so now in this case, we still have something where the model is almost the same. It's just got this kind of early layers to it, which kind of has a pre-trained job to do in our neural network. And it's nice because we know that if we pre-train these early layers, these very deliberate layers of our neural network, they tend not to change because neural networks are very, very lazy. So if these vectors are coming out informative, the rest of the model in theory is just going to learn how to correlate that with the specific task it has. All right, which is why we might train these layers one at a time. All right, this is an idea that was also kind of fairly classical in machine learning. The predecessors to neural networks, which are called deep belief networks, you have to train them layer by layer, right? Before Hinton figured out backpropagation, all these sorts of things, and even after backpropagation was figured out, while it was still computationally infeasible, they would train one layer at a time so that you could then get something like an embedding layer, and then you would take the embedding layer and learn another one and another one and another one until you were satisfied, and then after that you would just do linear regression. Okay, so this is a kind of foundational idea in machine learning. All right, if there's no questions on Elmo, we can move on to BERT. Yeah. Yeah. Because no, it's the number of blocks that you have. You have two of these highway blocks on top of each other.
So it's just that.
Yeah, so this thing would then produce another X, which would then essentially go back in here, and you would do it once more. Cool. Yeah, good question. Anything else? All right, let's look at BERT. So BERT is a bit weird. I must be honest with you. It is a strange architecture, but it's nice because it actually is really, really good at pre-training things. We will speak about another BERT architecture next week, which was tuned for African language, and it ended up being quite a kind of informative or useful model. So it's really good to know BERT. I think this is one of the ones where we really start to see the benefits of fine-tuning. And I think this is also one of the transformers that started to change people's mindset about how we should use pre-training and things like that. Okay, so this is a transformer. It is only the encoder side of an transformer, so it is not doing, it is not the full encoder decoder with cross attention. All right, we'll see now that that kind of distinction is a little bit fuzzy in this case. But the real reason this was useful is because it had a very specific set of tokens, and it had a very specific way of training that was actually pretty cool and useful. All right, so the model architecture is just going to take a transformer, and it's just the encoder. All right, and so what we're going to do is train two different objectives at once. All right, so we're going to do masked language modeling. So we've seen something like masked language modeling already. This is not the same exact thing because it's an encoder. We've seen masked language modeling on a decoder. All right, and then on top of that, we're going to do what's called next sentence prediction. And in particular, these two objectives are very easy to gain data for. All right, so again, we want to always be training on things where it's easy to get data. So for example, in last year's project, what I had everyone doing was we ultimately wanted to get a neural network that could decide whether or not to keep a paper inside of a systematic review. So that's something that medical communities do. It's like a literature review, but it's a little bit more strict in terms of the criteria of what gets included. And so if you're doing a systematic review of waste burning in Africa, right, like that was actually the topic they ended up doing, There is a very few set of papers that are highly technical, and it turns out that it's very difficult to train a model for this because that language is so specific and there are not many papers on the topic. However, you still want to do a good systematic review for it. So what they did, and what kind of some of the cool different pipelines they built up, was they first started by taking a pre-trained BERT model, right? So this model had been trained in this same fashion we'll discuss now to get a really good representation of language. Then they took the BERT model and they used it to classify medical versus non-medical papers. And there, all they did was scrape archive and scraped bioarchive. If a paper came from archive, it was considered non-medical. If it came from bioarchive, it was medical. All right, and they got a whole bunch of papers from it, and then they hit their neural network with that. All right, and it took forever to train, and everyone was complaining about the cluster. So we don't do that anymore. But it was at least really cool to see that that actually did lead to a very good downstream effect, where we then switched the task from being medical, non-medical classification to being include or not include in a medical review, right? And so there was a bit of interference there that like subsequent task had to forget that some of the medical language should be included, right? So it took a little bit of reversal to ignore some of the prior training, but the representations they got were useful, and the representations they got was because it was really easy to scrape archive and bioarchive. Okay, so this last point here, to make that point in a long-winded fashion, that point there is the key bit of BERT, right? You want to do things that are really easy to get data for. Okay, so this is the inputs to BERT. So there's a few familiar things and one unfamiliar thing. So we have our token embeddings, that's normal, right? So that's this layer over here. And you're going to also have things like separated tokens. You'll see that actually your project setup follows this pretty closely as well, right? I also have things like separated tokens and classified tokens, and we'll speak about the classified tokens now. Then you have your position embeddings at the bottom, right? That's that bizarre set of sine waves, except in this case, BERT, and this is important, BERT did not use a fixed position embedding, all right? It did not use the sine waves trick. It allowed you to actually back propagate that information all the way and learn the position embeddings. Now, you might then say, well, what makes it a position embedding? What made it a position embedding is because it was using a one-hot representation. Again, it was doing this embedding mapping off of the index 0, 1, 2, 3, 4, rather than using the index of the word in a dictionary, right? So then it is purely just a spatial thing that it was learning, and it learned that, kind of in its own embedding layer first, and then they added them together afterwards. And then lastly, they had these little tokens that was either A or B, depending on which side of this middle separator token it was on. Okay. Lastly, that's all the input. Then lastly, it also had this CLS, which was a classification token on the left-hand side. All right. And so that gave BERT this really unique representation, which was a classification token followed by a bunch of tokens for one sentence, then a separator token indicating that that sentence had ended, then, or it was kind of ending in the input at least, then it was a second sentence, a second string of words, and then lastly another separator token. All right, this gave a whole bunch of flexibility to what they could do with this model. All right, the fact that you had things like separator tokens and different sentences and stuff like that made it particularly useful. All right, so those are token separators, pairs of sentences, and usually you want to try and get it to be, you design your data set to either be 50% of them are consecutive sentences and 50% are just random pairings of sentences. And that was important because that was one of the tasks they ended up doing. Okay, and that is what this early CLS token was used for. It was used to predict whether or not the two sentences made sense in sequence. All right, that's this NSP objective, the next sentence prediction objective. That is a really, really difficult task. It's a very difficult task because it requires you to understand language semantically, and it requires you to be able to compress that or use that across entire sentences. It is very much like the same idea of word to vec, what it's doing on words, where it's predicting the subsequent words around a context word or a focal word. Now you have something more like a focal sentence at the front. You're predicting whether or not the next sentence makes sense to follow it. All right. And again, when they trained it, they balanced it so that you didn't run into like imbalance issues and stuff like that. So 50% of your data had sentences that made sense in sequence and 50% didn't. They then trained this classifier token here to predict that. It's not used red. This classification token here was then predicting whether or not those sentences made sense in a row. Okay, and then lastly, they had a masked language modeling objective, right? And so what they would do is they would take roughly, sorry about that, they would take roughly 15% of the tokens that were coming into the model, right? So let's say that these three red words, let's for argument's sake say that that's roughly 15% of the words coming in a sentence. You would pick them randomly, and then of those 15% of tokens coming in, 80% would be replaced by a mask token, right? So that's over here. Another 10% would just be replaced by a random token there. So you can see the word gray just gets mapped over here towards T. All right? Obviously, that's now going to break the sentence. And then lastly, another 10% were just kept the same. So mapped over here stays mapped over there. All right? Bit of a weird last thing to do, but that's what they did. All right? With 10% probability, you could still keep it the same token. And then what they made the neural network do is reconstruct or kind of re-predict the old words that were now corrupted. All right? If you've done computer vision, this is very similar to the augmentation strategies you've seen there, where you might put like a little block over a part of the image, you know, like if you're learning these clip embeddings, if Richard's gone through that with you yet, you'll do things like rotate the image or put a little block over parts of it. You'll do occlusions. That is the language equivalent to those sorts of visual corruptions. We're now doing these semantic word level corruptions. Mask, in this case, is then semantically meaningless. It can be anywhere in my sentence. So my neural network has to just learn to reconstruct that information. This 10% of a random token is actually more harmful because it can change the semantic of my sentence. But then from here, the neural network has to learn to repredict those same words. And you can see in this case why you want to also have this last 10% staying the same, because that allows you to just learn a very simple mapping from word to word, right? It can also train it to not completely lose word information. And if you are kind of in the early stages of training, that is a useful task. That essentially works like an autoencoder, right? You just want to take in a word, pass it through a set of layers, and be able to repredict that same word. All right? So there is an implicit curriculum coming in through these three different tasks or different ways we corrupt the data here. And again, a curriculum is a way of showing information which helps guide the representations we learn. All right, let's take a break there. I can see we're on 1 minute past 11. Yeah, we'll continue talking about BERT when we come back and then wrap up. Guys, I'm just going to mute you for 10 minutes and then I'll unmute before we start.
Where it says like that most and gets 80% of the time, and then I got 10%, and then solve 10% of that per 15%. Or the size that's split, because it feels like if that is the case, then it's not 80% of the time. That's like in this case, yeah, it's like the master's ones.
Yeah, it's within the 15%.
No, it's like that's within the 15%, so it's only like those ranges. But if you look at it, if you have 10 worth, 8 of them should be balanced.
Yeah. No, I get what you're saying. Yeah, I mean, sampling. This was just so that we could show the 3 different versions.
But it's like it is actually like that.
Yes.
See, like,
Mask. Yeah. And if you look at your whole sentence, 15% times 80% will be mask.
Okay, so these are actually like this is just
Example purposes, right? Yeah, that's true.
unmute on that button when you did.
Thanks for good catch, dude. Yeah, I've unmuted already. Oh, I made sure I was muted there. It's meant to be muted there, yeah, or else we get the squeal between the two. No, I muted so that conversation wasn't going to, if there was anything, it wasn't going to be recorded. It's a bit rough when I put it on YouTube. You like guys like, oh, it's this shit. Don't prepare me for my job at Deloitte. Can't believe it. That's now on the recording though, so Devin's in trouble.
Devin's the best.
Yeah, compliment me on the recording, please. I get like viewership randomly from like random people who then comment. They're like, and if I like don't upload quick enough, like you guys think like you're demanding. If I miss an upload, like your viewers were like, "Where's your new video?" I know you do NLP in November. I'm like, sorry. Right. Does anyone have anything to bring up before we get started? Cool. All right. So that's BERT, and I'm going to start off with a question. Why would we call this an encoder? And this is a hard question, but if you get it right, this means you've probably understood everything up to now. So we're doing masked language modeling, right? Which we saw was a property of the decoder side of our general transformer. So why did we say that BERT was the encoder of our transformer? What one property of our encoder does the BERT have that a decoder wouldn't? A hard question, so give it a sec. Guys online, you can answer as well if you are excited to. If there is genuinely nothing in your bag and you're just acting this out, so you don't have to look at me, that is great. Right, what do we know? What did we know about our encoder with the transformer in terms of the way it did attention? Okay, let's take one step back. What did we know about our decoder in the way it did attention, right? The way it implements masked language modeling. Could it look ahead in the sentence? right? We switched that attention off, right? We gave it a 0 weighting deliberately on that first layer of our decoder. Okay, the embedding, sorry, not the embedding, the encoder side didn't have that. It could do self-attention, forward and backwards. Let's use a different color. Forward and backwards over here and there and everywhere. It could look at the entire sentence because it encodes our context. It's the information we know we are given all of it up front, right? Okay. So because this is only masking individual words within the sentence, it's not predicting the next word. Do you think you're going to do attention across all words at once? Is it full self-attention, or is it going to have to mask the attention of the next word? This is binary, so you guys can just shout. You have a 50% chance of being right. Yep. Sorry? Yes, correct. Right? Because you're getting all of these words at once. We are putting a mask token in there. We are swapping words out, but we are processing the whole sentence at once, right? In which case, we're not going to be masking the next word. We're not doing the language modeling part of it. We are doing the encoding part of it. All right? And so in that case, this is now an encoder. The primary distinction between your encoder and your decoder in the transformer is whether or not you do self-attention between all words or you do self-attention only going backwards in time. Reason being is the decoder is doing your language modeling. It is producing the words, whereas your encoder is not. All your encoder has to do is give you token embeddings at the end, and it can use all of the words, all of the other words to do that. Right? That is the key distinction in our transformer. And so because BERT can self-attend across all words, it is an encoder. All right, let's look at some of the tasks we can do with this. All right, so number one, you can just forego the second sentence, even though it is pre-trained to do this language modeling kind of word imputation step. And even though it is trained to then predict whether or not the two sentences are kind of sequentially make sense or follow from each other, when we fine tune it, you don't have to use the whole architecture. And that is really, if the one point you take away from the BERT architecture is the fact that the way it was trained and the way it represented the tokens allowed a really wide degree of downstream tasks, then that is the key bit here. All right, that's the one thing you need to remember. The way it was trained supported many downstream fine-tuning tasks on BERT. All right, for example, you can do binary sentiment classification, right? You can do the COLAS task. So say whether or not a sentence is linguistically acceptable in its own right. And again, the reason you can do these classification tasks is because you have a way of taking in a representation and you have a way of labeling it off that class label, right? You then just have to do a little label off of that token there. And then hopefully because that token was already being trained to be predicted from, it means that it is actually going to learn to be useful for prediction tasks. Whereas every other embedding here is being trained to predict the word, the next word that came in from it, all right? Or the try and re-embed the word that it's representing, okay? So because we trained a classifier token, it means that it's now hopefully going to be good for a general set of classification tasks, okay? In a similar vein, this means you can still use the fact that there is the separator token. So now we can do tasks that require two different types of sentences. For example, you can do entailment classification. So if given a pair of sentences, say whether the second is an entailment, a contradiction, or neutral. So you can start doing things that are a little bit more logical. So it was pre-trained to say whether or not the sentences following each other make sense. Now it's trained to say whether or not two sentences that don't need to be sequential still logically follow from each other. All right. You can do core question pairs. So given two questions, say whether or not they are semantically equivalent. And then there's the last task, which says given two sentences, return a similarity score from 1 to 5. All of them can be done from the general classification token. Why? Because that general classification token was already trained to be useful and represent the entire representation of our sentence. Right? And because we've already trained our embeddings to understand the distinction between two sentences, because it has the separated token over here. Okay, we can also use the language modeling side of it, all right, the actual embedding side of it. So for example, there is a squad data set. So that's a data set with pairs of questions and passages, and then the passage needs to contain the answer to the question, and you need to indicate where that answer starts, right? So this, again, this is really cool for things like medical applications. You will say, does Jonathan have lung cancer? That's a question. Sorry, to Jonathan. And then you'll pass in a passage, which is the write-up from, let's say, a consultation with the doctor. And then you have to outline the range of tokens where that information is answered, right? So you can help now extract information from a broad set of information, right? So from a broad set of language. You can highlight the little piece of language where you can determine that Jonathan has cancer. And in these tasks, it can become somewhat arbitrarily deep. You're not just necessarily, obviously, if the sentence says, sorry, Jonathan, you have cancer, then it's going to highlight that. But also you can get to the point where it is understanding medical jargon, right? And it says there is a nodule at the top left of your lung, right? And then from there, it can understand that that is the region of the sentence that entails the answer to the question, right? And so BERT allowed for all of this, and it allowed for these kind of arbitrary tasks off the top of its word embeddings, its updated word embeddings, and the classification token. So that was the really cool thing about BERT, and that's also why most of these models nowadays are still BERT related, is because it was just such a foundational model. But again, the idea is that it's doing a lot of things, right? That takes a lot of data. But the tasks that it's pre-trained on are really easy to get data for, all right? And then on top of that, transformers are highly parallelizable, and you can hit it with bunches of data very quickly. All right, so again, the idea that comes to an NLP is that it's not necessarily about doing something mathematically or architecturally extremely clever. Sometimes it is, but also it's about doing things very generally that support very rapid computation. The more words my model sees, for whatever reason, the better it gets, all right, which somewhat contradicts all of statistics, but it's just an empiric fact that we're starting to understand. Okay, so to summarize, BERT has no task-specific model at all. In reality, what you're going to try and do is reuse the token embeddings that it has for your downstream purposes. That makes it useful. We can have a note on GPT, but obviously they don't do GPTs anymore. GPT was the other idea. So this is a decoder-only model. So you are going to be training on sequences of masked self-attention, all right? And you just do, in this case, it's 12 blocks of it. So you just do repeated masked self-attention, and then coming off that layer, you are doing your text predictions. So you are doing the language modeling side of it. Hence, it is a decoder because you cannot look forward in your sentence. All right, but then on top of that, they could then train a little bit of a text classification module off the last bits of the layers or the last set of embeddings. What this meant is that when they wanted to do downstream tasks, the GPT, or at least these 1, 2, and 3 versions, the earlier versions, you had to be a little bit creative. So for example, you can do classification just using the linear mapping off of the last layer of your transformer. But if you wanted to do multiple choice, you would then have to read in all of these sentences in a very specific way, right? Where you would show it the context and then the answer, right? With a whole bunch of delimiter and extract tokens around it. Then you would also show it the context again and the answer, and the context again and the nth answer. And because it was doing language modeling, you needed to keep re-showing it that in context so that it had this when it got to the point it needed to represent answer n. All right. You had to then always do the sequential rollout so that you had all the information necessary coming in the end of your transformer. And then you would show it all 3 of your options. And then from those last embeddings, you would then do a linear map off of those embeddings and get a softmax distribution, and then you can do your answering. All right. But because it was the decoder only, it was a little bit more restrictive. So they had to be more creative in how they showed it data. But it turned out again that reuse of the model for multiple choices, or if you're doing similarity for doing multiple sentences with the same transformer, again, that helps you train. Reuse is always going to make parameters learn quicker if it doesn't interfere with the actual model itself. Okay, and again, you could do things like entailment. So if you showed a premise and a hypothesis, the behavior of it is that it's going to do masked language modeling on that input, but by the end of it, again, because it has to do the masked language modeling, you will get a good representation that you can then do classification off of. Okay, so GPT, BERT, you are the encoder side, GPT, you are the decoder side, and because then decoder is masked language modeling, you need to reuse the transformer for multiple pieces of text depending on your task. Okay, let's move on to adapters. We are actually probably not making the best time today. Okay, so this is a different idea or a different way of now doing fine tuning. It's a little bit more of an academic one. And in fact, if you keep going in kind of academic NLP, it is very, very likely you will use adapters, and in particular what is called LoRa, so a low rank adapter. So this is very, very parameter efficient. Okay, so fine tuning, what we're going to do is we're going to obviously show our model a whole bunch of information, right? And we're going to start changing the parameters. The problem with that is that this leads to forgetting of language and things like that. So for whatever reason, when we start doing classification tasks with language, the model implicitly forgets how to actually generate or how to speak language. All right, this is a big issue and one of the primary areas of research that people are trying to fix. Okay, the idea here then is that we're going to use what are called adapter layers. And so we're going to fix the parameters of our model. All right, so hopefully that means that this layer is not going to interfere with its ability to do language modeling or its ability to represent language broadly just by trying to do a particular downstream task, all right? So there is a backwards compatibility to our model now, because all we're doing is going to insert this adapter layer and then train that to kind of fine tune to our task, all right? So if we're looking at our transformer layer over here, all we're going to do is after our feed forward layer, you're going to slide in an adapter, all right? Same story here. You have another set of feed forward layers, you slide in an adapter. It's technically, because it's multiple layers, it's called a module, all right? A set of layers. Okay, importantly, it happens before the skip connection in your transformer. So again, the skip connection, if that's what you want, the skip connection can still just keep the representation the same over there. What's nice though is because we're only training a module, we have fixed our attention, we fixed the first feed forward layers, you fix the second set of feed forward layers after the layer norm. What that means is that actually you're only now changing 1% of your parameters for the fine tuning step, right? 1% being roughly the number of parameters in the adapter relative to the rest of the model, right? It's about 1% of the size of the rest of the model. And so let's look at what an adapter module looks like. So this here is coming from there, all right? What we're going to do is you're going to take your vector representation from your feed forward layer, what would go into layer norm, and you're just going to pass it through a down projection, all right? You're going to have to compress that vector representation into a really, really small latent space. You then do your normal nonlinearity, probably a ReLU activation, and then from there you project it back up to your desired original output space, all right? So what happened if all we're really doing is projecting it down and then back up to the same dimensional vector? Are we actually doing anything? The answer is, well, we could be. It depends on what the task needs. But because we are passing through a really small, low rank hidden layer, all right, this really kind of small embedding or kind of latent space, then what that means is that there's actually not much we can do. We are limited in the capacity of this module to make changes. And so hopefully that's going to push it to only making the most important changes possible. All right. That means that it now has a pressure to be efficient in what it represents. And also it just means naturally that this down projection here, that's a small matrix and that's a small matrix. All right. So we're not adding a bunch of parameters. But really what the big pressure here is to be efficient in how it updates our vector representation. And that's all there is to it. All right. You just take this module. It's 2 new layers of weights. All right. Not very big ones. And then that is the only thing that gets updated with gradient descent when I move to my new task. Okay, so that's small. It's only a few new parameters that you need to fine tune. And again, you put these twice in an attention block. Cool. Those are trained. Everything else is fixed. Does that make sense to everyone? I think it's a fairly straightforward machine learning idea. Okay, so for every new task we're going to do, you're going to stick 2 new layers in your adapter layer. You stick 2 new layers of weights, and that's the only thing that gets fine-tuned to actually perform a task. And again, because it's a small hidden layer, it has to be efficient and it has to use parameters wisely. There are some other directions to this going on, and I'm going to speak about one of the more recent ideas now. So, for example, you can talk about how do we do design training objectives that work well. We spoke about BERT being a really interesting set of training objectives that required it to learn good semantics for language as a whole. How do you go about fine-tuning these things? How do you go about adapting? How do you modify it to a new task, and so on? I think there's some cool ideas sitting here with continual learning and LoRa in particular, which I'm going to speak about now. But yeah, so it's kind of an active area of research, and this is maybe one of the first cases in this class where we actually are now at the forefront of NLP. What I'm going to chat about now is LoRa. So this was actually done by a past student who is now your tutor. His honors project was on LoRa, so I let him make the slides. He got 5% for the class from it, so he was happy. So the background to LoRa is that, okay, we've now decided that these adapter layers, this kind of efficient small sets of parameters that we kind of update to allow it to change the model for a new task, that seems to work really, really well. But there are some downsides to just a straight LoRa, right? So this is background that we've already covered. So the problems with the original LoRa is that you still have to do it sequentially, right? So while it was parameter efficient, you still have to then pass a vector representation, go down into this kind of funnel network, and then have to produce it back up, right? Now, LoRa did a different thing. What it would do is you would take the same exact input in on the right-hand side, all right? So you would usually go through your pre-trained layer on the left here, okay? But now what we're going to do is we're going to pass it through a parallel stream, all right? So it's not sequential like a normal adapter. What it is instead is going to go through a different layer of weights. And this is going to be denoted by our delta W. So what change in the weights we would want, okay? Now, in theory, when I'm fine-tuning a model on a task, what it's going to do is it's going to take my initial weights, all right? You can represent this as the initial weights, plus the change that would have happened from that fine-tuning, okay? If I'm just doing it straight, if I'm just doing the straight kind of fine-tuning without an adapter layer, what I'm going to end up with is this W prime inside of my layer of weights, right? That is just my initial embeddings, my initial weights, plus the change necessary to fine-tune. So what we're going to say is, okay, we're going to make that split explicit. It's not going to happen implicitly in the layers of my neural network. I'm going to actually represent it as this kind of addition of two matrices, all right? Your immediate assumption would be true. That is bad, because now I have double the number of parameters. So what we're going to do is instead, we're going to try and represent this change matrix in the most efficient way possible, all right? Then I'm going to freeze the pre-trained weights, all right? So I'm going to freeze the model architecture that I have. It's still going to do matrix multiplication. It's still going to do its forward pass and give me part of my output. But now I'm going to pass it then through the changed weights as well, which would allow me to update my output of my layer, and then I add those two things together over here. Okay, mathematically, this requires the linearity of matrix multiplication, which we know to be true from our previous studies in mathematics. You know that you can split matrix multiplication around addition at the very least. It's distributive. Okay, so mathematically, this is completely equivalent, but it gives me a lot of control in how I update my weights. And so what we're going to do now is do a low rank approximation to that delta W, all right? So instead of representing delta W as some matrix multiplication D by K, all right, depending on the two sides of the layers I'm mapping to, we're instead going to represent it as the product of two different matrices, B and A, all right? If you think back to singular value decomposition or Kolesky decomposition or whatever decomposition you had in mind, you will know that we can represent delta W by this product over here. So the sizes will stay the same, right? We still have a vector that is D by 1 in this case, being multiplied by 1 by K, which will give us a vector or a matrix which is D by K. But now the important thing is that it is low in rank, right? The rank there is 1. It doesn't have to always be 1, but it has to be low, all right? What that means is that now there is a limited amount of change that I can make to this, this matrix. It has a null space. There are certain things, there are certain parts of my input that it cannot work on. A matrix multiplication that is low rank will have what is called a null space. which means there is part of the input which it maps to 0. In other words, there are some X values here that when I pass it into my adapter layer, it will output 0 here. In other words, it keeps it exactly the same as the pre-trained output. Okay, that is the key step here. The fact that this delta W is now deliberately low rank means that there are inputs that it will never change the output for. Okay, the number of such inputs depends on what rank I pick, how I pick this little R value over here and over here. Okay, and so instead of learning delta W, I am now going to train B and A with gradient descent. It will need to learn the parameters of B and A that when multiplied together give me the best delta W possible. But instead of having 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 25 weights in delta W to learn, it has 5 plus 5 weights, which is 10, obviously. And so now it has 10 parameters to do this change in W learning rather than 25. And so now it is hopefully going to be a lot more efficient and easy on memory. And so this is how it ultimately looks. All right. I took my delta W that was over here. Okay. And I now have my 2 forward passes over there, which is A and upside down B. Okay. That means, again, the key bit here, the fact that it is low rank means that there are things it cannot change. And so ultimately, when I want to compute the change in my weights, there is now W0, which is the pre-trained full rank weights, plus this low rank approximation to my fine tuning. Okay. And so hopefully now what that means is that there are aspects of the prior pre-training that W0 will not, where W0 is the only thing that gets maintained, and BA will not interfere on that part of the task. And so hopefully we can still keep reusing that information. Is this actually going to help us? Well, you can do the maths, and there's an example in the slides of this. So in reality, we would have had to do, let's say, a D by D matrix multiplication. So that's D squared parameters. But if we do LoRa with low rank approximators and our R is set much, much smaller, then the number of parameters you're going to have to work with is actually D by R plus D by R. Okay. E. And so you get 2 D times R. All right. If your R value is much, much smaller than D, if you're going through a very low rank approximation, then you're going to be much, much more parameter efficient. You guys doing right there? Yeah. Is there a question? I'm genuinely asking, like, was that a question? Yeah. Okay. So that's the foundations of LoRa. There's an example here. So let's say D is 30 and K is 10. Then if I was learning that matrix multiplication, I would have to use 300 parameters to do that mapping. But if I factor the matrix and I have a rank of 2, then it turns out I will only need 80 parameters, right? D will be 30 up top there, K is 10, and then this is 2 and 2. So we end up with 30 times 2, 2 times 10, which then is much, much smaller. All right, it's the main idea. Again, I'm sure you guys understand factorization and stuff from second year linear algebra, but it's the main idea of why we want to keep things low rank. All right, they make them much more efficient to remember, and you can do things like compression and so on. It's the same idea as like principal components, for example. Okay, so while matrices A and B do not capture all the information about delta W, the LoRa method is effective due to its intrinsic low rank, and it means that you will at least capture the most important parts of that mapping. Okay, and so then they showed that the kind of original LoRa paper showed that they could fine-tune GPT-3 to get equivalent performance, or at least even better in some cases performance, on a whole bunch of tasks with like a fraction of the number of parameters, right? Like a really, really small amount. Okay, so it's faster, it saves computational resources, it means you have to train less parameters, and you can combine it pretty easily with pretty much any architecture. Reason being is because it is just another matrix multiplication, it's just a low rank one. And so, you know, matrix multiplication is the foundation of all we pretty much do. All right, and so in this case, you also don't always have to do LoRa all of your layers. You can LoRa some of them. You know, a lot of the times you can maybe say that I want to do this low rank approximation only in the deeper layers of my network where my embeddings should be changing to be a bit more task specific, but the early layers that are a lot more general should be staying the same completely. In that case, you can make it even more efficient by keeping most of the architecture frozen and then only doing this low rank approximation or low rank adapters on your kind of readout layers. And so you end up with this spectrum on the right here of how big is the rank of LoRa versus how many layers I fine tune with LoRa, and you can actually get really, really efficient from it. In general, the rank is usually set to 8, but again, that's going to be a hyperparameter you need to tune, which is the one downside of LoRa. It is sensitive to this hyperparameter. All right, the rest of this was a bit fluffy, so I'm going to skip it. Essentially, you can do kind of LoRa on vision tasks, and one of the cool things is they did it with stable diffusion as well. And so you got a model that's good at generating paintings. You can then do a little bit of adaptation to do things like style transfer and so on. And so you can kind of actually get a really, really good amount of style transfer, something that's quite impressive, but with only a little amount of changes to your layer. Okay, everyone comfortable with the idea of LoRa? Okay, pretty foundational. You just split your matrix into the pre-trained part, the adapter part, or the kind of changes you want to make, and then you make the changes low rank. All right, that is the full derivation of it. And then the benefits is that, number one, low rank means it has a null space. There are parts of the input it cannot change. All right, in other words, it maps to 0. And then input or benefit number 2, it is more computationally efficient. That is the full summary of LoRa that you need. If you want to write that down, that is coming up. Cool. All right, and then the somewhat mundane repetition of what we've seen before. How do you analyze these things? Can we determine that pre-training with BERT and things like that is useful? And it turns out yes. So you can do your more model-specific interpretations. So you can look at the components of the model. For example, you can look at what the heads of a BERT multi-head attention is doing. You can do the model-agnostic approaches. So you can probe linguistic structure. Can you predict things like parts of speech from the embeddings and the tokens of your BERT model? How does that compare to classical representations from NLP? How does it compare to things we know a language model should be learning? So for example, one of the things they're applying over here in the classical NLP pipeline is that there was a kind of taxonomy of what you needed to learn in a language model or to model language. So for example, you would need to understand nouns before you could understand noun phrases. All right, so noun phrases are things like the yellow brick road, right? You have to understand it as a monolithic entity if you're going to understand the sentence. But first you have to understand what yellow means, what brick means, what road is, right? And so that was a kind of curriculum or a sequence of things that needed to be learned in an NLP pipeline. And it turns out that you can actually show that the embeddings of BERT, as the layers go, it actually matches what we would consider an appropriate NLP pipeline. The first layer is able to predict things like nouns. The second layer is able to represent noun phrases and so on. All right, then lastly, you can also look at the predictions on other tasks and you can evaluate it for specific phenomena. So for example, you can use BERT as a knowledge base, and I think this is one of the more fun ones, which we'll see now in a second. But let's look at the attention heads that came out of BERT. And this is going to be important for next week as well when you talk about AfriBERTA, the African language BERT. So you might want to keep this in mind. So if we look at the attention heads, there was always an attention head trying to keep track of where our separator token was, right? So that was there. So it turns out that it realized the separator token was a really important thing for doing this next sentence prediction task, but it also realized that the distinction between the two sentences was going to be useful for most contexts, for most tasks we did. And so it would always have these two bits of attention that were just keeping track. Where does one sentence start? Where does the other end? That is really, really useful to do, right? On the flip side, there is the stuff that we saw last week when we were looking at transformers, where they also like to look one word forward or one word back. So you would get these diagonal patterns of attention, where it was trying to keep track of what the most important words in kind of the vicinity of your current word was. You would get mixtures of it. So token embedding, attention heads that were looking at multiple types of words in your sentence and trying to use the combination of them to be informative. You got this block attention representation where it was now being a little bit more specific to attending to the entire first sentence. and attending to the entire second sentence. So here your first sentence is there. All right, it's all got some degree of attention on it. And then the second sentence over there is your getting your second block of attention. Again, a slightly harder question. Does anyone want to tell me intuitively why they think the bigger block would be dimmer than the brighter block with the attention there? Guys online, I think maybe it's your turn to answer this one. Why do you guys think that the smaller attention block in this attention head is slightly brighter than the bigger one? What part of attention is going to dim a larger number of words? I'm gonna be honest, I'm gonna end the lecture now if someone doesn't actually just try. I'm kind of tired and over it. So does someone want to hazard a guess, or can we just call it for a day there? No? Right, no one cares. Right, thanks guys, I'll see you all next week.